Hello and welcome back. Today we are talking about radioactive decay. Now, I am sure that you probably heard the term radiation before, but you might not have learned about the specific kinds of radiation that is involved in nuclear physics, and that's what we're going to dive into today. So we talked about atoms and isotopes in the previous video, and what we learned is that atoms can come in different varieties, and different numbers of neutrons produce different isotopes. Now, most of the atoms that we interact with are stable, which is to say they are going to last a very, very long time, many of them longer than the life of the entire universe. But some isotopes are unstable. When we say unstable, what we mean is that given the chance, or perhaps even just over time, some of them will fall apart. And when they fall apart, they will emit nuclear radiation. Now, it is important that we differentiate between different kinds of radiation. We talked about electromagnetic radiation in previous units. That, light waves, that is radiation. But when we talk about nuclear radiation, we are talking about radiation that comes specifically from the nucleus. So it's not caused by just moving electrons and orbitals around and that sort of thing. That's a different kind of radiation. So these unstable isotopes are called radioisotopes. Now, just to give you a sense of how this works, if we take a look, if I make an atom, a very simple atom with one proton, then I am making hydrogen. I've got hydrogen 1. And you can see here that on this chart, whatever half-life means, we'll get to that in a minute, that it is very, very stable, that it has a half-life that is very, very long. Hydrogen will last the life of the universe and more. If I try to add another proton to build a different atom, it's not going to work. I can't just make helium by squishing two protons together. That is not stable. That won't even form in the first place. But if I add a neutron first and then add a proton, that neutron is enough of a mediator. It helps generate enough strong nuclear force that those two protons can actually stick together. And of course, I could have helium-3, or I could add another neutron and have helium-4. And so you can see that helium-3 and 4 are both stable isotopes of helium. But if I keep on adding protons and neutrons, I eventually get to beryllium-8. Now, beryllium-8, you can see on my slider here, is way down on this side. It is very unstable. Its half-life is in the tiniest fractions of seconds. And so this is not a stable nucleus. And what that means is that over time, in this case a very short time, the nucleus is going to fall apart. It is going to emit radiation that makes a more stable nucleus. In this case, we're going to do something called alpha decay. And so when I click this, it fires off radiation, and what's left behind is now a stable nucleus. Now, if this nucleus wasn't stable, then continuing reactions could happen. You could have more and more nuclear interactions to eventually arrive at a stable nucleus. So there are three kinds of radioactive decay, nuclear decay, that we're going to look at. Three types of emissions. Okay, the first is an alpha particle. Now, an alpha particle is two protons and two neutrons. Okay, it is essentially a helium nucleus. So it's helium with a mass of 4 with two protons and a charge of +2. There are no electrons. Alpha particles are fairly large as far as particles go. They're small, but they're fairly large compared to other particles. And they move fast, but again, relatively slowly compared to other types of radiation. Okay, so alpha particles, when they emit, they can go through paper or maybe like thin cardboard or sheets of wood, but they're going to get stopped by thicker materials than that. Now, beta particles are essentially a high energy electron. And it's important to notice here that a beta particle is an electron that comes from the nucleus. And you might be saying to yourself, this guy's crazy, electrons are not in the nucleus, they're in the orbitals around the outside, and you're right, they're also there. If you take an electron that's in an orbital and you just knock it loose with a bit of energy somehow, that is not a beta particle. That did not come from the nucleus. We're going to learn that, in fact, electrons can actually spring into being from the nucleus in the form of a beta particle. And the last one is gamma radiation. Now, gamma radiation is just really, really high energy electromagnetic radiation, EM radiation. So we learned about gamma radiation before. It's at that far energy scale of the electromagnetic radiation, but it is the same thing as light and radio waves. It's just very, very high energy. And of course, it comes from the nucleus in this particular case. So you've got a highly energized nucleus that emits a burst of gamma radiation. So, as I said, there's kind of those three kinds, and we're going to look at some nuclear reactions to kind of see what happens when each of these radioactive decays occur. So the first one is thinking about alpha particles. So if you have a radionuclide or a radioisotope that has too many nucleons in it, it's just too crammed in there. It's too busy in the nucleus. It can get rid of 2 protons and 2 neutrons at the same time by emitting an alpha particle. So an example of that is plutonium-239. So plutonium-239 has the symbol Pu and a mass of 239 and an atomic number of 95. Now it's going to undergo an alpha particle decay, and let's take a look at what that looks like. So I've got some plutonium here. Very big nucleus, one of the largest stable nuclei, or relatively stable nuclei that we find, but this is pretty busy, right? And this is going to want to decay. So when I do alpha decay, let's take a look at what happens here. When I give off an alpha particle, I lose 2 protons and 2 neutrons. So you can see that I actually change elements because I'm changing my atomic number. So I fire off 2 protons, 2 neutrons, and now I'm left with something called uranium-235. So I produce uranium-235, which has atomic number 93 plus an alpha particle. And a reminder, the alpha particle has a mass of 4, and it has an atomic number of 2. So the first thing to notice is that the number of protons and neutrons is still conserved. So the number of protons and neutrons, my nucleons, don't disappear. When I have radioactive decay, they exist still, they've just been split apart. So 239 total nucleons, I can see they still add up, and 95 total protons, those still add up as well. Okay, so the next one is beta decay, and this is kind of a weird one because we're talking about electrons that are coming from the nucleus, which we didn't think they had those. So an example of beta decay is carbon-14. So carbon-14, the symbol for carbon-14 is C with a 14, and it has 6 protons. And so let's just think about what that looks like. So if I've got, let's say I've got, I want to make carbon. So regular carbon is going to have a total of 6 protons and 6 neutrons, and you can see that it's quite stable. But if I was to go ahead and pack a couple more neutrons on there, you can see it's a little bit less stable. So this radioisotope is going to decay at some point. Now, what's the problem here? Well, carbon-12 was plenty stable. It was a good ratio, a good balance of things, and it turns out that if I add too many neutrons, I can become less stable, right? I kind of need a balance, a certain balance of protons and neutrons. And so this is going to decay, but what does this need to do? Well, this needs to get rid of a neutron. And here's the weird thing, is it doesn't just take the neutron and fling it loose, it undergoes beta decay, which looks like this. Have a close look. So I click beta decay, and it emits a beta particle, but all of a sudden it turns into nitrogen. So this, I'm going to rerun that, it goes from carbon-14 and it turns into nitrogen-14, which that's kind of strange. Okay, so let's think about this. I had carbon-14 and then I decayed into nitrogen-14. Well, nitrogen has 7 protons, and so I've increased my number of protons somehow, but I've also emitted a beta particle, which is a high energy electron. Now, the only way for this to happen is I keep my nucleons the same. I have the same number of neutrons and protons total, but I add 1 extra proton. And don't forget, this negative electron came out of somewhere. So what actually happens in beta decay is a neutron splits. A neutron splits, emits an electron, and turns into a proton as a result. And while the mechanism for this is pretty complicated, hopefully you can see that that's going to do 2 things. One, it's going to conserve the total mass of the nucleus. I'm not changing the mass because I'm just swapping a neutron for a proton, but it also conserves charge. You get rid of a negative thing and you create a positive thing, and overall that is still neutral, which is what the neutron originally was. So during this process, a neutron is converted into a proton, and so therefore the atomic number increases. Okay, it increases by 1, and the mass number stays constant. Okay, so beta decay is a little bit strange because it actually comes in 2 forms. It turns out that there is something called beta minus decay, and what we were just looking at was beta minus decay, but there's also something called beta plus decay. And I want to talk about beta plus decay. Okay, so two forms. So beta plus decay could happen to something called carbon 10. So if I have carbon 10, so a total mass of 10, but again it's carbon, so I've got six protons. So if I go back here, let's make some carbon 10. There's carbon, and if I take away 2 neutrons, again you can see that I've become unstable. Well, the problem here is now I've got too few neutrons, right? I've got more protons kind of than are willing to hang out together, and I don't have enough neutrons to mediate them. So what would be really nice is if I could get rid of a proton, and this is how we do it. We don't remove a proton, but instead we emit a beta plus particle. So beta plus looks like that. So let me go back. Beta plus turns carbon into boron. So I go from carbon 10 into boron 10. And so what I've done essentially is I've gone from carbon into boron 10. Now boron has 1 less proton than carbon, so it's atomic number 5. And what I've emitted, and this is weird, is a beta plus particle. But a beta plus particle is not an electron, it is actually a positron. It is a positive version of an electron. Now it turns out, spoiler alert, that all the matter that we see and interact with and the atoms and particles and things we've been talking about actually comes in kind of 2 varieties. You have matter and you have antimatter. And antimatter is exactly the same as matter. It has the exact same particles, and that standard model we looked at with the quarks and the gluons and the leptons, you have a matter and an antimatter version of all of those things. The difference is they have the exact opposite charge. So an electron is matter and it's got a negative charge. A positron is antimatter and has a positive charge. And other than that, it's exactly the same. It has the same mass and all behaves in the same way, but it's got a different charge. So by emitting that positron, what have we done? Well, we have taken one of our protons, and the positron is a positive charge that's left, so what it leaves behind is a neutron. So during this process, a proton is converted into a neutron. And again, hopefully what you notice is our mass number stays conserved. We don't gain or lose nucleons. We don't destroy matter, but we turn a proton into a neutron, and so our atomic number is decreased. And even though we decrease our atomic number, notice that we keep our charge constant, right? We haven't gained or lost charge. So as if beta decay wasn't weird enough, there is another wrinkle to add on top of all of this, and I'm sure you were hoping that it was going to get more complicated, but too bad. That when scientists first discovered a beta decay, both plus and minus, when they ran the numbers on it, they noticed there was a little deficiency. And so when you take all of the things you start with, and you find all the mass and energy of all the things you start with, and then you take all the things you end up with, the daughter nucleus and the positron or the electron, and you add the energy and the mass of those all up, you're short something. So it turns out that these particles, the momentum and the energy of those interactions were not conserved. And so scientists suppose there must be some other particle that we are not quite noticing. And this particle is responsible for some of the energy and momentum in the system that they could not observe. And so they predicted that there was this particle called a neutrino. And neutrinos have almost no mass. They're very, very, very small in terms of mass, and they have no charge. And on top of that, they travel at nearly the speed of light. So with these neutrinos, they're so small and so fast and uncharged that they're actually very, very difficult to detect. But lo and behold, after they were predicted, some years later, scientists were actually able to detect these things. And so we now know that for beta decay to happen, it has to include a neutrino. So the way it works is, if I have a parent nucleus that has a mass of A and an atomic number of Z. When I undergo beta decay, we know that I'm going to get a new nucleus that has the same mass number, but I'm going to lose one of my protons. It's going to turn into a neutron. I'm going to emit a positron, a positively charged electron, if you will, plus I'm going to emit a neutrino, and the symbol for a neutrino is this one. And so this is my neutrino. Okay, and so that accounts for all the energy and momentum that we would expect to see. The flip side of that is my beta minus decay, where I'm going to start with a parent nucleus, and I'm going to create a daughter nucleus that has the same mass number but one more atomic number, because remember, I'm creating a proton, if you will. It's going to emit an electron, a beta minus particle, and it is going to emit a neutrino, but this neutrino is an antineutrino, which is, you guessed it, just like a neutrino, but the opposite in some ways. And so matter versus antimatter. So the thing to remember is that when you produce an antimatter beta particle, a positron, you produce a matter neutrino, and then vice versa. When you produce a matter beta particle, a beta minus, then you produce an antineutrino. Now, the last one, luckily for all of us, is maybe the simplest, and that is gamma radiation. So gamma radiation is just a situation where the nucleus has a whole bunch of energy in it. Typically what happens is if I have some other kind of radioactive decay, the daughter nucleus might be still energized by the result of that decay, and then it needs to release that energy somehow, and sometimes it's going to release it as a photon of gamma radiation. So because we're emitting light, because we're emitting electromagnetic radiation, the atomic number and the mass of the nucleus doesn't change because it's just energy. It's just light. And so if I have an example of barium-137, barium-137, and that's number 56, if I want to indicate that the nucleus is in an excited state, I just add an asterisk here, okay? So that means that I've got an excited nucleus, and then it's going to emit that radiation, but nothing is going to change in terms of the mass number, and nothing is going to change in terms of the atomic number, but I am going to emit some gamma radiation as a result. And again, that's just high energy photons. So with all of these reactions, nuclear reactions, a lot of the laws and so on that we learned before are still going to hold true. Like, for example, the conservation of charge still exists. So the total charge of the system must be the same before and after the reaction occurs. You can't generate or destroy charges. Also, there's conservation momentum. So both linear and rotational momentum is conserved. If a beta particle goes shooting off that way, that's going to cause the the daughter nucleus to move in the opposite direction, for example. Now, in addition to that, most of these interactions, they're generally elastic, or at least very, very close to, and therefore kinetic energy is almost always conserved by these interactions. And then the last here maybe is somewhat new, is this idea of we conserve our nucleon number. This is basically conservation of mass. And so the products and reactants of any reaction will have the same total number of nucleons. Essentially, we're not going to destroy our nucleons. We might transform them, but that's it. And so this constrains the number of possible reactions that can occur. Not every possible decay is possible for each given nucleus. Now, the other thing to consider is that that when we talk about momentum being conserved, what we're talking about is the center of mass of the system. If I have a particle that splits into two parts, then the momentum of the center of the mass of the system is conserved. So center of mass really is just like the average location of all of the mass in the system. So I'm just going to call this the average location of the mass of a system. Now, if I want to calculate the average location, the way we do that is we say that the location, at least along the x-plane of the center of mass, so you could do this in the x or the y or the z, whatever you like, but for the average location of the center of mass in the x-plane, that is going to equal the sum of all the individual masses and positions divided by the sum of all of the masses. Okay, so if you imagine you've got a bunch of particles in a system, if you find their location and their mass, you multiply them together, add them up, and then divide by the total mass. That tells you your position. So imagine we've got this. We've got a thorium-232 atom sitting at rest when the nucleus ejects an alpha particle. Now, sometime later, the alpha particle has moved 100 nanometers from where the decay occurred. Where is the daughter nucleus at this time? Okay, I've got my thorium atom located here, and that's got a mass of 232, and essentially what's going to happen is it is going to eject an alpha particle. So the alpha particle is going to come, let's just say it gets shot out this way, and so my alpha particle goes there, and that has a mass of 4. And so as a result, what am I going to produce, and where is it going to be? Okay, so when I have an alpha particle emitted one way, then the parent nucleus that goes the other way is going to have 4 less mass and 2 fewer protons. So it's going to be number 88, which is something called radium. So radium with 88 and then a total mass of 228 gets ejected that way. So we can see that essentially our center of mass initially was just located right here at some 0 point, right? So our initial center of mass, let's say, is located at 0, and then at some point later, this is 100 nanometers away. So where is this other daughter nucleus? Well, if x, the center of mass, is equal to the sum of the individual masses times their positions divided by the total mass, the center of mass initially is at 0, and it needs to stay at 0 in total. Each particle might move, but the total center mass of the system is still going to be at 0. So I can actually eliminate this and solve and say then my center of mass, the sum of my center of masses times their positions, must add up to 0. So this is like m1 position 1 plus m2 position 2 must equal 0, which means the position of particle 1, let's say that's my radium, the position of particle 1 is going to be negative m2 position 2 over m1. Okay, so this is like negative 4 is my mass times 100 nanometers divided by the mass 1, which is 228, and this ends up being like 1.8 nanometers and negative because it's in the backwards direction, which kind of makes sense because the daughter nucleus is so much larger than the alpha particle, but it would have shifted a little bit, but not that much. Okay, so now we need to talk about how this decay occurs. Now, as we said before, the radioactive decay is measured in something called half-life. And it's called half-life because there's no way to know exactly when a particle will decay. The actual decay itself is random. It's like tossing a coin or rolling a dice. But what we do know is that if we have enough particles and we measure them over a long enough time, we can get an idea of how long it would take for half of them to randomly decay, right? Just like if I gave you 100 coins and told you to flip 100 of them, I would have a pretty good idea after you flip them all that you would have about half heads and half tails. So because of this randomness, we can only measure the decay in half-lives, okay? And so you can see here in this graphic, I've got a full sample at some point in time. Well, after one half-life, half of the material has randomly decayed. After a second half-life, well, half of half has decayed, and so now I'm left with just a quarter of what I originally had. And it continues on to an eighth and a 16th and so on. And I suppose in theory this just continues on and approaches asymptotically. So the key here, of course, is that we're talking about large numbers of atoms. And because there's large numbers of them, it's actually quite predictable how long it will take for this process to happen. So the half-life is the time it takes for half of a sample to decay. Okay, and so to go from a full sample to a quarter would take 2 half-lives, and to go from a full sample to an eighth would take 3 half-lives, and so on. Okay, so we need to talk about something called mass energy equivalence, and that is going to link into this whole nuclear decay conversation that we've just been having. So when Einstein discovered special relativity, it led to some really interesting conclusions, which showed that as an object increases in speed, and we're talking about very high speeds here, as a particle gets closer to, say, the speed of light, its mass actually increases. And the only way that this could make any sense, that as an object has more and more kinetic energy, it doesn't just gain speed, but it is also gaining mass, is to be that mass and energy are somehow equivalent. And what Einstein was able to prove is that mass or matter is actually an equivalent form to energy. And he expressed this in his very famous equation, E equals mc squared. Okay, and I'm sure you've seen this before. But in this case, E is energy, and m, of course, is mass, and c is the speed of light in a vacuum, right? 3 times 10 to the 8 meters per second. Okay, and so what this implies is that in certain situations that matter can actually be converted into energy and vice versa. And this might seem to fly in the face of some really important laws of physics that we've been hammering on this whole time, like the conservation of matter cannot create or destroy matter, and the conservation of energy cannot create or destroy energy. And it turns out that those are still true, but they're actually all part of one overall conservation of matter and energy. Now, these particular situations, they happen only under certain conditions. You cannot just take like your coffee mug and turn it into pure energy. That's not going to happen. But we do notice, especially when we look at these nuclear reactions, we do see situations where matter just seems to disappear and all that's left is pure energy. So a really good example would be in like a nuclear reactor, okay? If you have a nuclear reactor, you might put in 1 kilogram of, let's say, uranium and put it through a process to harvest the energy from it. When it comes out the other side, the byproducts, when that has all gone through a whole bunch of decay processes, you're only left with 0.999 kilograms. Now, that's almost all of it, but there's something missing. And what's missing has been turned into pure energy. So you could calculate this and say that the energy released is equal to mc squared. Now, the mass is 0.001 of a kilogram. It's just 1 gram. But we're going to multiply that by 3 times 10 to the 8, and then we're going to square it. And that is a huge, huge amount. That is actually 9 times 10 to the 15 joules. So just 1 gram of matter got turned into 9 million billion joules of energy. That's an incredible amount. So you can see that it doesn't take much matter to create a lot of energy. And it would take a lot of energy to just create matter. But we can actually create matter in specialized circumstances, like in particle colliders and these sorts of things, where we do a lot of the research that we do on particle physics. So when you think, another way to think about this energy, mass energy equivalence, is if you start building atoms, like let's say we just give you protons and neutrons and electrons and you just start building atoms. If you want to make a helium atom, you might take 2 protons and fuse them to 2 neutrons and then throw in 2 electrons in orbitals around it. What you would notice, though, is if you were to weigh all of the ingredients, all of the protons and neutrons and electrons before you make the atom, and then you weigh them afterwards, and you would notice when you add them all up, the total mass of the original ingredients would be more than the mass of the final helium atom. Well, what happens there? Well, when all those ingredients come together, some of the mass is converted into energy. Now, this should not be a huge surprise because helium as an atom is very stable. And when we say it's stable, what we mean is it is at a lower energy. So 2 protons, 2 neutrons, 2 electrons would prefer to be a helium atom because that is a more stable, lower energy configuration for that matter. Now, this mass defect explains the stability of the nucleus, right? The reason the nucleus stays together is because it has released energy and become more stable, okay? And this energy is known as binding energy. It is the energy that is released by the formation of a nucleus, okay? Now, the binding energy, you can think of it 2 ways. It's how much energy gets released when you form the nucleus, but that is also related to how much energy it would take to destroy the nucleus, right? So the binding energy is also the amount of energy needed to break the nucleus apart, right? Because that's how stable that nucleus is. All right. Now, one last thing we need to talk about is fission versus fusion. I know this is the thing that sometimes gets a little bit misunderstood, and I think it makes sense is why it would. You may have heard of these 2 kinds of reactions, fission reactions and fusion reactions. Fission reactions is what happens in like nuclear reactors, where we take things like uranium and use it to produce useful energy. And fusion is what happens in things like stars, when nuclei bomb together and they stick together and they release a ton of energy. So fission involves the breaking apart of larger nuclei. And fusion involves the fusing of smaller nuclei. Now, where I think these two get a little bit strange is both of them produce a ton of energy. And why is that? The key is in what type of nucleus you're talking about. Let's talk about fusion first. If I've got, say, deuterium atoms, so hydrogen 2 atoms, and I fuse them together, I create helium, which is more stable than those original atoms were on their own. Since they're more stable, they release energy in the process. Small atoms coming together make a more stable, larger atom. But with fission, when we think about fission, we have these very, very big atoms like uranium or plutonium. And those atoms are less stable in that configuration. When they break apart, they actually become more stable. What this hints at is that atoms kind of have a sweet zone. When atoms are very small, they'll fuse together to make larger atoms and become more stable. And then when atoms are very, very big, they'll break apart to make smaller atoms to become more stable. There's a sweet spot on the periodic table somewhere around iron, where that is like one of the most stable configurations for a nucleus. It's got just the right amount of nucleons, but not too many, and it's still stable overall. Okay, that is it for nuclear radiation.